Hello, everyone, and this is yet another technical walkthrough call, which is a part of the series of technical walkthrough calls of Ethereum Attackathon. And today we're joined by Matt from Reth Project, one of the projects, again, which is like part of the scope of the Ethereum Attackathon. Matt has come prepared today. He's going to talk about the structure of the protocol, known issues, interesting points for you guys, for whiteheads, where to hunt, where not to hunt, and everything like that. So Matt, please take it away, and thank you so much for joining.
Thanks, Tim. Maybe brief introduction on me. I've been working on the Reth project since the beginning, and I will go over the most interesting components today and what to keep in mind when researching or finding bugs. So let me quickly share my screen. All right, you should see the repository. Okay, let's start with the GitHub repository, which has a bunch of stuff in there. We can likely start with some links. We have a user book, which is for actually running the nodes and interacting with RPC. It contains all the instructions, how to set it up, building it from source, using pre-built binaries or Docker. We have some developer documents which go over the design, the repository layout and structure. And it also contains some code snippets that are unfortunately a bit out of date. So we are revamping a lot of stuff at the moment. So let me quickly go to the crate section, which describes all the crates on a high level and includes some code snippets that make it easier to understand. Those might be out of date, but should help get you onboarded. And for the actual docs, we have rendered crate docs. So this is a list of all the crates in the repository, and you can navigate to those that you're currently looking at. And you see all the rendered docs that are also part of the code itself. And then you can also navigate to all the other components. So this is for docs. About layout, as mentioned, we have a bunch of crates. The way the repository is structured is that we have a lot of modules. For example, we have few things for network, P2P implementation, peering, types, and we currently support Ethereum and Optimism in the same code base, which use a lot of shared code. As you can see, there are the modules that are abstracted in such a way that we can use them for both Ethereum and for Optimism. And for the Attackathon, there are a few things to keep in mind. So most interesting is likely the engine API implementation, which is the critical component that advances the chain. At the moment, we have two implementations of the engine API. One is a complete rewrite, and the other one will be deprecated soon, which the legacy implementation is composed of those two crates. And for the Attackathon, I would recommend looking at the new implementation. Yeah, the most critical or bug-prone components are related to networking and engine API. For networking, we have discovery. I put here some instructions or overview about the components. All of this is also documented in the code itself, but these are the selected crates that are most critical, I would say. So first ones are for discovery. And for discovery, you can use the dev P2P tool or Hive for testing, for example, to verify everything works. For the actual network implementation, which is the component that does all the P2P stuff and transaction gossiping, all of this is implemented in the Reth network crate. We also have this rendered as stock. And you can also navigate on the docs page or via the clone repository. So the network it does all the peer management, discovery, and also downloading of the blocks itself, the headers and the bodies. And it handles also incoming requests. The protocol that those components implement is the RLPX protocol, which is defined in the Ethereum Dev P2P spec. And everything is basically RLP. So there have been some bugs in the past. So especially because we have a lot of manual RLP implementations, worth taking a look at those. I also listed some important dependencies here. And the way things interact with each other. So the way the networking is run is that is spawned on a separate task. And we do a ton of message passing across the entire repository. So the way things communicate with each other is with so-called handle types, which are basically just channels that emit a request event, for example, and await the response. For example, if you want to download a certain range of headers, then we would send a request to the network task and then await the response. The heart of the project really is the new engine implementation, which is included in the Reth engine tree crate. And what this does is it advances the chain driven by the consensus layer and the engine API. So the way this works is that we have exposed an RPC server, and the consensus layer sends us the requests for a new payload. We verify that payload, convert it into a block, keep it, and verify it, and wait for the next fork choice update. which would then trigger a new head block, or effectively a new head chain in case there is a reorg. And the way syncing works is that when we initially boot up the nodes, we wait for the first fork choice update and try to find out what the latest finalized block is and compare that block to our local head in the database. If the distance exceeds a certain threshold, we enter what is called pipeline historical syncing, where we essentially download the missing range of headers and blocks, execute all of those, and try to catch up with the tip. When we are close to the tip, we enter LiveSync, which is then processing blocks as they arrive and extending the blockchain with the new blocks. The way blocks are persisted is done asynchronously. So when we receive the fork choice update request, then we check that the head hash that is part of the request matches a block that we previously verified. If that's the case, we respond immediately, and we schedule this new head block for persistence. So persisting is we write this block to the database, and until it's persisted, it's still in memory, which is shared also with other components, especially with the P2P layer, which also needs to access the latest state, for example. So there could be some race conditions there, especially if we consider that this has to be synchronized with some mutexes. And all of this are memory operations, at least for the in-memory block range. So they should be fairly cheap, but there could still be some deadlock potential, I would assume. Okay, if we go to persistence, all of this is handled in the background and is also triggered by message passing. I will go over this entire workflow in the code in a bit, but I just wanted to set the stage first. Yeah, persisting is done in the background. We have two separate data storage. One is a key value database where all the Ethereum state is stored, and then we have what is called static files, which are immutable append-only storage location for transactions, headers, and bodies, because we don't expect any changes there once they've been part of a block. And yeah, this is again for networking, which now links to the protocol itself. For crypto-related issues, there's only really one library that we implemented, which is for authenticating the RLPX P2P sessions. This has been audited before, but worth also looking into this again, because the implementation is not that straightforward. Right. So where you should look for bugs is some issues with async code, especially deadlocks. Like if we have a non-blocking Rust task that could potentially block indefinitely. That would be a problem. Reorg scenarios are also complex, and there could be some edge cases, and of course consensus bugs, and for the networking component always DOS or some peering issues. Yeah, these are the most interesting crates I could think of. I mentioned that Reth has been audited before. This was done by Sigma Prime, I believe 6-8 months ago.
Were there any interesting findings in there, Matt, in the audit? Like anything that you want to raise?
Yeah, the usual suspects, P2P related things. I mentioned reorgs, a few critical ones. Let me go to the overview. Yeah, state root calculation, or with the most recent new transaction type, some RLP decoding stuff. Engine API, and networking again. So this audit covered the older Engine API implementation. I mentioned that this is composed of these two crates, which we have since entirely rewritten. So I would expect that we might have similar issues as discovered here, like skipped state rule validation, for example, for previously downloaded blocks, something like that. But yeah, the report is public in the audit folder, worth checking out. And I think I'll go over the crates I mentioned and cover the entire life cycle of one block, basically.
Yep, makes sense.
All right. You can see my screen, right?
Yes, everything is good. Yep.
Cool. So I start with the entry point for the consensus layer requests, which is the Engine API implementation, which receives the RPC objects. And those are for the next block or the new payload. This is the execution payload and some additional fields. We do some pre-processing here, like some sanity checks on the format, basically, like if it complies with the spec before we actually send it off to the engine implementation that is capable of executing the block. So all of this is done via message passing. So in the request context, we send it off to the tree implementation, which at its core is just an endless loop that receives or awaits the next engine message and then handles this message. So the Engine API request can be like a fork choice updated, or it can be the new payload, which includes let me zoom in for a bit. The payload, the sidecar, which includes all the additional fields that are not part of the actual execution payload. And then one channel where we will send the results back to the engine RPC handler, where we await the result here. So when we receive the new payload, we try to execute it according to all the consensus layer specs. So first we ensure that this is a valid block. Then we do all the necessary checks to make sure the payload is actually a new one and hasn't been submitted before as an invalid block, for example. And then we do a lot of checks and try to insert the block into an in-memory section if it's actually valid. So we have some cases where we inserted a valid block, or we already know this block, or there are cases where we received a new payload which is disconnected from the local head, which means that we might need to download this block from the network. And on new fork choice update, we received the new state, which includes the head hash, the latest finalized and safe hash. And we start processing this in a similar way. So we make sure that we have a new fork choice head. And if we have this head, if we have this block already, then we can actually make this canonical. So what making canonical means is that we have a new block, or maybe even more than one block, in case there is a reorg that goes one block back and two blocks ahead. And when we have a new canonical chain, which is one or more blocks, then we can mark this as the latest block, so the highest chain that we have, and update everything accordingly. We emit a few notifications, which are important for things like WebSocket subscriptions, for the new head event, for example, or to update the in-memory state with the latest canonical chain. Well, I haven't talked about persistence yet, so if we go back to the main loop, then we have another check for advancing persistence. And what this does is it checks if we have more than a certain amount of blocks in memory. If we have like 3 blocks in memory, then we can start persisting those. And persisting is handled on a separate thread, which is also similar to the engine implementation, which is also effectively just a while loop that waits for incoming commands. And then it handles this command, like it stores a certain amount of blocks on disk and sends back the response after it committed those blocks. And on the engine implementation side, we will receive this response and can update our canonical chain accordingly, basically advancing some pointer that tracks the highest, the chain height that is on disk and the chain segment that is stored in memory. So this is the life cycle of an engine API request. I briefly touched on the case where we might need to download some stuff from the network. And all of this is implemented in the networking, in the network thread. So what happens here is that what happens if we have a missing range of blocks is that we first need to download this missing range by issuing requests for the header and the block bodies. And the network task is also effectively like a loop. Let me find it. Yeah. Just scroll on. That advances some state. So it's basically also waiting for incoming requests, for example, like downloading blocks, sends those to peers, awaits the response from a peer, and sends it back to the engine implementation. We have very high-level docs on all the components in the network implementation. We have some examples here, how to use it manually. And we describe it from a bird's eye view. We have actually 3 separate tasks on the network side. One is the actual network implementation that drives peers. And then we have 2 separate tasks that handle requests from other peers, like fetching headers and serving them back to the peers. And for the transaction gossiping part, we have also one separate task that does the same thing and is also wired to the transaction pool. Like we receive propagated transactions from other peers, we delegate those to the transaction pool, or we receive new transactions from the pool and need to broadcast those to peers. Right. For the network, we have a few Mermaid docs. They should be rendered on the docs page as well. So you should see how everything is wired together with all the interfaces and how everything is wired. So worth taking a look at the rendered docs as well. Yeah. I think that's mostly it for the critical components. So we talked about the entire engine API lifecycle, how it is connected to the network, and how we do a ton of message passing. So I would expect that there might be some edge cases where we have issues with blocking futures or something like that. So worth exploring if this can be exploited by other peers. Like if you trigger something from on our end, and we run into some weird edge case where we panic. So we should definitely not panic anywhere in the networking part. If that is exploitable, that would be a severe issue.
Makes sense. Makes sense. Thank you, Matt. Anything else?
I think that was mostly it. Yeah, I would suggest or recommend checking out the audit report first, or looking at previous bugs that were discovered during the audit, and maybe map it to the code and take it from there. For testing, for network testing, we have a lot of end-to-end tests where we can create actual multiple network instances and can then communicate between those peers and issue commands. So this should be, in case there's an issue, it should be possible to come up with a POC relatively easily.
Mm-hmm. Yep. Got it. Wonderful. I think that's also everything, that we can get from your side. So, unless you have some final words, some, I don't know, words of encouragement, I think we're done.
I'm excited about upcoming bugs. And
right. Of course. All right. Then thank you everyone for watching. Whoever got to this point of the video, and good luck with the Attackathon. I mean, of course, if you're watching this one, the Attackathon is live, and it's still live till January 20th, up to 1.5 million in rewards. So go grab those rewards and submit bugs. Thank you, everyone.
Awesome. Thanks.